Namaste and a warm hello to all of you. I hope you all are staying safe during this pandemic. Today, in the next 10 minutes, I want to share an update with you regarding a method I presented in SciTech last year. This method, called the Uniform Trigonometrization Method or the UTM, uses trigonometric functions to impose different types of control and state constraints for complicated optimal control problems. Now, this has been published recently in the Journal of Spacecraft and Rockets, so you can read more about these complicated problems and how UTM solved them. But there is a very unique set of optimal control problems that have not yet been solved using the UTM, and these are the mixed constraint problems. As the name indicates, a mixed constraint expression comprises both the states and controls. While using indirect methods, traditionally one has to formulate and solve complicated multi-point boundary value problems while dealing with mixed constraint problems. The motivation behind using the UTM for such mixed constraint problems is to solve a much simpler 2-point boundary value problem, so that we don't have to deal with multiple arcs, but we can just deal with one arc and impose the constraint at any number of places, and we just have to think about the initial point and the final point. But the real challenge is, how do we convert the mixed constraint expression into a trigonometric form? To solve this challenge, let's look into two types of mixed constraint problems. The first type involves linear controls in the mixed constraint expression. This can be simply solved by reformulating the mixed constraint expression such that we have constraints purely on the controls. Note that the bounds on the controls are of variable nature because they depend on the states. However, the focus of this study is another set of problems where the control appears in a nonlinear form in the mixed constraint expression. For such problems, we need to convert the mixed constraint expression into a pure state constraint form using a 3-step approach, which I will be sharing with you through a hypersonic example. So consider a hypersonic problem with a G-loading constraint. The objective of this problem is to maximize the kinetic energy of an impactor. The dynamics of the problems are given by these equations. Some useful expressions used in this problem are shown here. Note that the angle of attack is the only control that is present here. The boundary values of the problem are defined in the table on the right, and the constants used in this problem are defined on the left. So these are based on the impactor as well as Earth as a planet. Now this problem we cannot solve using the UTM right away because the G load here is of a mixed type, and what happens here is that when we start using the UTM, we have certain expressions of this angle of attack in a polynomial form and some expressions in trigonometric form. So overall, the control law becomes transcendental in nature. The details of this are present in the paper, so I encourage the audience to go through the paper if they are interested in reading more about this issue. But that's the basic reason why we need to, first of all, reformulate this problem so that we can even use the UTM. So for that, we use the 3-step approach. The first step is to use the original control alpha as a new state. In the second step, we choose alpha dot as the new control, which is more realistic in nature. We also write alpha dot in a trigonometric form such that U trig actually now becomes a new control. So we write it in this way and we can impose any realistic bounds on it. Here for demonstration purposes, I've chosen these values, but we can always change them. Using steps 1 and 2, we have converted the original mixed constraint problem into a pure state constraint problem. The optimal control problem is now reformulated to implement the pure state constraint on the G loads and to also account for the bang-bang or singular form of the new control, which is alpha dot. We then find the new Hamiltonian and thereby find the control law for the new control, which is U trig. So this is the Euler-Lagrange equation, and these are the two options for our control law. Since there are more than one options, so we need to employ something called Pointryagin minimum principle, which says that we need to choose that control which gives the minimum Hamiltonian from among these two options at each instance where we calculate the trajectory. Finally, we also obtained the new co-state equations of motion corresponding to the new state alpha. We solved two different types of G-loading problem, and here I'm sharing case 2, which is a more interesting one. In this case, the hypersonic impactor has a fixed initial flight path angle of -45 degrees. This forces the impactor to dive into thicker parts of the atmosphere, thereby leading to high G loads. Since there is a G-load constraint, the vehicle is forced to skip to the thinner parts of the atmosphere, which are at higher altitudes. Then the impactor dives back because the ultimate objective is to hit the ground. So especially in the last part of the trajectory, there is a deep dive, which is expected. This approach overall helps in maximizing the terminal energy while satisfying the G-load constraint, which is of mixed type. The results from the UTM are found in excellent match with the corresponding results from GPOPS2, which is a very popular software based on something known as pseudospectral methods, which are direct methods. The angle of attack rate here stays within the bounds, as you can see on the plot here. They never attain the maximum values or the minimum values. But the interesting part is that the G loads are actually hitting the upper bounds in the initial part of the trajectory. This tells that the UTM can successfully solve the mixed constraint problems of actually any type. And instead of solving this as a multi-point problem of 4 points, we can just have one single arc comprising initial point and the final point. In summary, two types of mixed constraint problems were shown. For mixed constraints comprising linear controls, we need to convert the mixed constraint into a pure control constraint form. And for problems involving nonlinear controls in the mixed constraint expression, we need to convert them into pure state constraint form. Only then we can use uniform trigonometrization method. For this latter, we need to use a three-step approach, which I showed through a hypersonic G-loading problem, where the G-loading constraint is of a mixed type. Two types of this problem were solved, and I showed the results of a more interesting set, in which the results obtained using the UTM matched very well with the pseudospectral method based solver called GPOPS2. As a future work, our team would still like to solve a certain set of mixed constraint problems where there are linear controls in the mixed constraint expression, but these linear controls also have constant bounds on them. Also, the continuation strategy that is used in this paper needs to be automated for the uniform trigonometrization method. So thank you so much for your time, and if you have any questions, we would like to take those.